Well, I don't know if it's brilliant, but thanks. Yeah, so I had this talk prepared, and then last night, just before going to bed, I was thinking about all the great talks that we heard yesterday, and actually had some idea inspired by the talks yesterday, and I think I'd much rather tell you about that because it's a much more interesting result than what I had planned to do. So there's a risk that there's a bug and someone will find it, and I promise beer if someone finds a bug, and then this would be a little bit embarrassing, but I think with the audience here, it's a much more interesting result to tell you about than what I had planned to do. So this is a little bit improvised and not prepared at all, but let's try. Okay, so what I'll be talking about is, of course, conditional lower bounds. And so from the talks yesterday, it's sort of clear that we had all these different conjectures that you could use to prove lower bounds. So there's the combinatorial Boolean matrix multiplication conjecture. There's the Seth and threesome and let's say APSP. And also each of these conjectures were used to prove lower bounds for different problems, right? And it sounded like we even needed to have even more conjectures to capture all of P, right? That was sort of the impression I got from Amir's talk. So what I was trying to think about is if some of these conjectures imply each other, right? It seemed like a natural question, and I think other people have been looking at that. And that's not exactly what I managed to show, but so the result is here. So if BMM is true, so combinatorial Boolean matrix multiplication requires n to the 3 minus little of 1 time, then there's no n to the 3 half minus epsilon threesome algorithm. And I want to say combinatorial. Okay, so at least if it's true, there's some progress towards unifying some of these conjectures. Okay. So if there's no combinatorial Boolean matrix multiplication algorithm running in n to the 3 minus c, then there's no threesome algorithm that's combinatorial that runs in n to the 3 half minus epsilon. And of course, the conjecture for threesome is n squared. So this is off. An interesting thing is that the decision tree complexity of threesome is in fact O of n to the 3 half, as was shown by Seth and Alan Fox last year, I think. So maybe n squared is not the right answer. I don't know, but at least this shows that there's some connection between the problems. And I think this was more interesting than what I had to tell you about otherwise. So this is like the first implication. I think the second one, there's one more implication of this stuff, which is not quite as interesting as this one. But the second one is, under the same assumption, combinatorial Boolean matrix multiplication is true, then there's no n to the 3 half minus epsilon 3 orthogonal vectors algorithm. That's combinatorial. 3 orthogonal vectors algorithm. So this problem has n cubed conjecture complexity. So this is not as interesting as the other one, but at least it shows some connection. So I'll try to see if I can convince you about that and myself. And I'll start with this one over here. Okay. So let me move over here. Okay, so just to summarize the problem, right? So combinatorial Boolean matrix multiplication, we have these two Boolean matrices, the n by n, and we want to compute the product. And so for this talk, I'll think about it as, since this is not a vector, but this is not a matrix, but essentially you have n vectors for which you want to compute mv. Okay, so this is m, and you have vectors v1 to vn. You want to compute each of these matrix vector products, which is obviously the same problem. Okay, it's just a little bit easier to think about. So the first step of this reduction is inspired by the nice paper by Monica Hensinger and co-authors, where they introduced this online matrix vector problem. So in that problem, they have this online matrix vector problem. You have the matrix, the Boolean matrix. Vectors arrive one at a time, and you have to output mv before seeing the next vector. Okay, so one of the steps they used in their paper to prove conditional lower bounds was that they first reduced this problem to another problem where you have vector pairs. Okay, so you have a matrix M, and then you see pairs of vectors. So you see u1, v1. You get n pairs. And for each pair, you're supposed to output ui transpose mvi. Okay, So this is just a number this time. And sort of the interpretation of this is, if you think of the matrix M, Ui selects a subset of the rows for which there's a 1 entry in U. Vi selects a subset of the columns, and then you're basically asking whether this submatrix that's induced by these rows and columns has a 1 in it. Right? That's exactly the question you're answering. Right? So is there 1 inside any of these entries? Right. So for their reduction, this is in the online setting, so these pairs arrive 1 at a time. So then we basically show that if you can do this in n to the 3 minus c, then you can do this in, I think it's like n to the 3 minus c over 1 plus 2c or something like this. Okay. So for Boolean matrix multiplication, up here we know all the vectors at the same time. Right? We have all the vectors available. And so basically the first step is to redo their reduction and show that you can reduce to the case where you know all the vector pairs at the same time. It's basically just going over there, reduction with a bit of care, and you can sort of do the same thing, right? So you can show that given all these pairs at the same time, if you can answer these vector matrix vector products in n to the 3 minus c time, then you can solve Boolean matrix multiplication in m to the 3 minus c over 1 plus 2c. And I think I'll show you the reduction at the end, but it's basically just the same as they do. So I'll get back to that at the end. The more interesting part is then how do we solve this problem using threesum. Right, so that's the interesting part, the new part. So let's try to have a look. Okay. So, yeah. So the first observation is essentially, which was inspired by one of the talks yesterday, is that if you look at, so now I have this matrix, and I'm looking at just one of these, answering one of these pairs. If you think about this, that if you think of having a graph, it has 1 node per row of M, and 1 node per column of M. Then this query over here, this question that you're answering, so if you pick every 1 entry in this matrix, so let's say in row I and column J, and you draw an edge between the ith node over here and the jth node up there, what you're asking is really, maybe I should take another color. So one of these queries, it just selects a subset of the nodes over here, a subset of the nodes up here, and then you're asking whether the induced subgraph has an edge or not. Right? That's the question you're answering, which is what Svi talked about yesterday. And so what Svi and Seth showed was that this problem is threesome hard. Okay? So it's threesome hard to report the induced subgraph under some setting of parameters. So here we basically want to reverse it, this reduction, which was inspired by what Emmanuel was doing yesterday. So he basically found a way to list triangles if you had an algorithm for threesome. So that's basically what we want to do here. So the first idea, so let me just show you the idea if you're just answering one of these queries. So the idea is, so let's first pick a hash function, essentially what Emmanuel did, that hashes these nodes of this graph to some big polynomial universe, let's say n to the 10. Okay? And now what you can do is, so you take each edge here, let's say it's between, now let me call them S and T, these 2 endpoints. So you take this edge, each edge is turned into a number in your threesome instance. Okay? And the number that you generate is the hash of S plus the hash of T. Okay? And so the version of threesome that I'll be looking at is this, you have 3 sets, you have A, you have B, and you have the sum set, and you're looking from 1 in A and 1 in B that sums to 1 in S. Okay, so that's the version we're looking at. So basically all the edges here would be the sum set. Okay, and they will be of the form, there will be 1 number per edge and it will have this form. Okay. Now, when one of these UIs and VIs arrive, intuitively what we want to do is we take all the numbers that are in my set of nodes over here, and then I just add to A is just the hash of all these numbers, all these nodes that is in my set, right? And up here, similarly for V, I just include the hash of all the nodes that are in my set. Then I get a set A, a set B, and the sum set. Okay, so what's the observation? So if there is an edge in this induced subgraph, the hash of the one endpoint is in A, the hash of the other endpoint is in B, and because the edge is there, the sum of the hashes is also in S. Right, so there is a solution to the three-sum instance. Now the second idea is basically because these hash values, these hash functions maps to, say, n to the 10, let's say it's 4-wise independent or something like this, then you won't have any false collisions with probability, let's say 1 minus 1 over n to the 5th or something like this. Do you believe this, or should we?
Yeah. But what I don't understand is the set S is going to be...
Yeah, it's going to be n squared, and the others have size n.
That's right.
That's right, yeah. So that's the next. This is just if you had only one UI and VI, right? So now I'm going to try to solve it for all these pairs at the same time. So that's the next step, right? This is just the intuition if I had only one UI and one VI that I was trying to solve it for. And this is why this stuff does not work for the online matrix vector problem. It only works for the Boolean matrix multiplication. Okay. Right, so now we have something, at least if I only had one UI and VI, I'd get a set here that has size n, and this would have size n, and this would have size n squared. Right, so the n squared here's the problem because it's too big compared to the two other sets. So what we want to do is, basically we want to do all these in parallel, all these pairs in parallel. Okay? And so for this, I have another hash function, g, and what it does is it basically maps an index from 1 to n. So this is something from 1 to n. And it also maps it to some really big range, let's say n to the 10. Okay? And now, what I conceptually do is, for each of these pairs, you imagine you have a copy of all these nodes. Okay, so this is like for the ith pair. This is for the ith pair. You have a copy of all the nodes, and you're selecting a subset of them. So basically, let's call, so the version of the, so you had a node S for a row here. So you have the ith copy of this S. It won't turn into the number hash of S, but it will turn into the hash of S plus g of I. So I have to add some part of the hash function that tells me which pair I come from. Okay. And so the same over here. So the one that comes from the ith subproblem, the ith vector pair, instead of doing hash of t, I do hash of t minus g of I. Okay? So what happens now is, if one of these pairs has the answer 1, there is an edge in one of these pairs, then this will have a solution. Right? So let's say the ith pair has a 1 in the submatrix. So you basically just go, maybe let's say that corresponds to the node S and the node T, and there's an edge ST in there. Basically what you observe is that the GIs cancel out because it's the same subproblem that you're looking at, and then you still have the same, that the hash of S plus the hash of T sums to this thing in here. Right. So what we've done now is, okay, so the GIs, so again we have to worry about false positives. So could you get false positive in this thing? And basically what we observe is that if you try to add if you try to use a node from two different subproblems, two different vector pairs, the GI and the GJ will be independent and they'll hash to something random that won't hit with high probability. So that's the intuition here. So what we can do now is, basically we can take this, we can take the three-sum algorithm. So what's the size of the inputs now, right? We had n pairs. So now A has size n squared, B has size n squared, and S has size n squared. Now they have the right sizes. So if three-sum runs in n to the 3/2 minus epsilon, what you do now is to answering this instance now takes n to the 3 minus 2c time if three-sum is in n to the 3/2 minus c. Right, because the input size is n squared. You're looking for a bound that's subcubic to solve this problem. So if three-sum is n to the 3/2 minus c, you get subcubic. So there's still one problem with this reduction up to now. What we get out now is just, basically we just told the OR of all these answers, right? If one of them has a 1, there'll be a threesome, the answer will be yes to the threesome problem. And otherwise, if none of them has a 1, it will be no. But we have to answer all of these pairs. Right? So answering all the pairs is the next step. And it just uses some of the ideas that have appeared before in many of these reductions. So basically we want to, the idea is that if you can change the threesome algorithm. So let's say if there is a threesome, you can also find a witness efficiently. Right, so this is not too difficult. You probably also saw it in Emmanuel's talk yesterday. So basically what you can do is you can partition A into 2 equal-sized sets, B into 2 equal-sized sets, and S into 2 equal-sized sets. You try all 8 combinations. If one of them must have the answer yes, and you just recurse on that one until you're down to finding a witness. Okay, so you can find a witness in the same running time because the subproblem sizes also go down by a constant factor. Right, so you can find a witness in the same running time. Is this clear enough? Okay. So you can find a witness. So the problem is, still right, so you find a witness over here. Maybe now you know that the pair UI, VI has the answer 1. So intuitively you can remove it and just continue on the remaining n-1 pairs. But this will take you too long, right? Because you'll need to do it n times to solve all these pairs. So essentially it's too expensive to find a witness and remove one of these pairs. So somehow we need to do something that we can find all these witnesses and not make it as expensive to find the witnesses. And this just uses some of the ideas that appeared in other work. So we just want to decrease the cost of finding a witness. So the idea here is to take your matrix M, and now you partition it into a k by k grid. So basically you have n over k by n over k submatrices. And now the intuition is that you just solve on all these submatrices one at a time. Okay, so what does that mean? So now basically we had all these. So this was V1, Vn, and you had the columns, the rows over here. You had U1, U2, Un. And now what you do is you start by looking at this first submatrix up here. So you're looking for witnesses inside this submatrix. Now, so you're looking for witnesses inside the submatrix. So this is an n over k by n over k submatrix. We already showed we could find a witness in n to the 3 minus 2c time, where n is the size of the matrix if you have equal sized, the number of vector pairs is equal to the number of rows and columns. The intuition is you start with the first submatrix. Basically you just cut these into pairs of groups of n over k vectors each. You just handle each of these groups on this smaller instance one at a time. Okay. So now you have this group here. You have n over k row vectors, n over k column vectors. And if you're in this submatrix up here, basically what you're using is only the first n over k coordinates of each of these vectors, right? And the first n over k coordinates of each of these vectors. Right, and it's the exact same problem that you're looking for ones inside this submatrix up here. Okay, so now we just do that using the threesome algorithm and find a witness. So the decision is if we find a witness, now we just remove the pair vi ui that caused the witness to appear, and we just do it again with the remaining vectors in the set until there are no more witnesses. And we do that for all the vectors. Then all the ones that we haven't found a witness for, we just move on to the next submatrix, move on to the next one, and the next one, and the next one. And clearly this solves the problem, right? So the question is just, how much time does it cost to do it like this? Okay. Now we need to argue that it's not too expensive when we do this. Okay, so let's try to argue that. So we already agreed that if we can solve threesome efficiently, then we can solve this problem in n to the 3 minus 2c time on an n by n matrix with n vectors. So You see what happens now. So for each of these submatrices, you have basically you have n vectors that you need to go over, so k times that you need to solve the subproblem of n over k by n over k by n over k, right, on each of these submatrices. And so solving all these, so the first run with a batch of n over k vectors, with n over k vectors with a submatrix, so you have one run at least for each of these groups. And so how many of these execution, what does all these execution cost? So right, we have k squared submatrices. We have k groups of vectors that we're solving on this submatrix, and solving a group costs n over k to the 3 minus c time, right, or minus 2c, let's say. Okay, so this is the cost of the first run inside a submatrix, right, the first time that you run it. So the thing was that whenever we found a witness, we had to repeat. Right? Whenever we found a witness, we had to repeat on the same set of vectors. So essentially, so we get a lot of repetitions, runnings of the algorithm again. And so what does that cost? So the observation is now this can only happen n times, right? Because once you found a witness, you remove the vector pair. You know the answer is 1. So basically, you have in total over the entire matrix, you have n of those runs where you pay again n over k to the 3 minus c time to do the run. Okay. Now we balance the two terms to figure out what we should set k to. And so what does this give? Yeah, so basically you have to set k to the n to the 1 over 3, right? Yeah. And so what is the running time that we get? Plot this in, so then you get n times n to the 2/3 to the 3 minus c. This one here is n to the 2 minus 2/3 c times an n. So basically we're subcubic now, right? So that's good. Solving all these subproblems in total cost subcubic time. So I guess the only thing left to do now is the first reduction from Boolean matrix multiplication to this batched, let's call it batch vector matrix vector multiplication. Do people want to hear this, or do we all know the bound by Hensing et al? Do it for completeness? Okay. Right, so the only step missing is this, from this version to this version. Or maybe, yeah, let's do that now. Okay. So the idea is sort of similar. So again, you take your matrix M, and you divide it into a k by k grid. And now, so basically you had all these n vectors that you're trying to compute the inner products, the matrix vector product. And what you do is you zoom in on one row. We call this a super row. So all this up here, this is a super row. It has n over k actual rows. And so now look at what were we doing for a super row. So the idea here is that, so let's again, so this is a subproblem of size n over k by n over k. And so now you group your vectors again into batches of n over k vectors to get the sizes to match. And now the idea, the really beautiful idea of Hensing et al. Is that so inside this subproblem here, you want to use these vectors u for something. And what you'll be using the u's for is, so you want to figure out which of these inner products, these n over k inner products, are 1. Right? And so the idea is, so let's say you have the first batch of n over k vectors, you want to figure out which of the inner products are 1 when you just look at this submatrix here. So this is the first part of the vectors against this submatrix in here. What you start by doing is that you take, so for each of these n over k vectors, you create a corresponding u vector. Okay, so this called this v1 to vn over k. So you create u1 to un over k. Initially, these are all ones vectors. Okay, so they're all ones vectors. And now, so the observation is that now if I run this batched vector matrix vector algorithm on these n over k pairs against this n over k by n over k matrix, I'll be told which of these pairs have, since the ui transpose this tiny matrix, let's call it, I don't know, M11 with the vi. So I'll be told all of these products. So basically I'll be told for each one of them if there's at least one of the rows in this submatrix that has the inner product 1 with my set of current vectors, right? For each of them I'll be told whether there's one of these row inner products that's 1. The idea is then you search for witnesses again. So once you take this group, you run this query against the submatrix, and you'll be told which subset of them that has an inner product of 1 with at least one of the rows in this submatrix. And the idea is, so you take the ones that does have such an inner product, and then you want to search for a witness. And this is what you'll use the u vector for, to search for a witness. So the idea is that you take all these n over, so there's some, at most, n over k vectors here that have some inner product of 1 in here. And what you do is, each of them has a corresponding u vector. Basically, and these u vectors have a bunch of 1s, which is essentially selecting the subset of rows that you're ORing over. So for each of them, you just arbitrarily partition the u vector into 2 halves, equal size. And now you run both of these batched matrix vector matrix vector queries for where you set all of them to the first half of their choice of 1s and to the second half of their choice of 1s. And then you'll have learned for each of them, you'll have learned one of the halves in which there is a witness. Right? Is this clear enough? Or should I repeat it again? So essentially each of these ones is selecting a subset of rows that we're ORing over. And so for one of these UIs, I arbitrarily partition these 1 bits into 2 halves. At the same time for all of these n over k vectors. I just choose the first half for all of them, and I run this batch vector matrix vector query. And that will tell me which of them that inside the selected half of the ones actually has a witness. Right now we're ORing over only half the number of rows, and we'll be told if there's a witness still. So essentially we learn for each of these n over k vectors, we learn which half has a witness. Maybe both of them have, but we'll learn at least one of the half that has a witness. And then we do this log n times to find a witness for each of them. Right, so we find a witness, which means essentially we've discovered for each of these vectors that had some inner product of 1 in this submatrix, we discover a row that has the inner product 1. And then the nice idea that you do is, essentially you just erase that 1 bit from u. You go back to the u you had before the binary search, and you erase that 1 bit, so that means now you're not searching over that bit anymore. And now you need a little bit of more care to get it to work probably here. So the idea is, when you're solving this subproblem here, so you take these n vectors that you get in, and partition them into groups based on how many ones they have found so far. Right? So there's only n over k rows here. So there will be n over k groups. So it's the potential of or whatever of these vectors. So there's a group where you found where you still can find up to n over k things, and then all the way down to this, it's not possible to find any more ones in this submatrix. So essentially your n vectors, you start by partitioning them into groups when you get to this submatrix based on how many ones how many witnesses it can find in total when you walk over this row. And so then the idea is a little bit more refined. You start by taking the larger of these groups, partition into batches of n over k vectors, and search for witnesses for the ones that have a witness in here. You update the u by erasing the corresponding coordinate, and then you move them down to the next, what you can call a potential group, right? So you know now you've found a witness, so there's at most n over k minus 1 more times you can find a witness while going over this entire super row. Right? This is basically what's going on, right? You can at most find a witness n over k times throughout the entire super row. Because once you've found a witness, you know already that you don't have to look in here to figure out what the inner product is, because this part over here already told you that the inner product is 1. And so that's the whole idea. So you just start from the first block in this super row. You find witnesses in the ones that have them. You move them to the next potential group. You take the next group and do it again. So you need to make sure that there are not more rows. One of these vectors could have inner product 1 with many of the rows, right? So once you've dealt with the first group of potentials, you take the next one, you move the ones down that actually where you found a witness, you take the next group, and so forth, all the way until they eventually end up in the last group, if they ever do so. Right, so once you've done that for the submatrix and there are no more witnesses left, you just move on to the next one in this super row, the next matrix. And you keep the U's because you know it's essentially the same rows that you're trying to figure out what the inner products are. It's the same set of rows when you're in a super row. So basically that's what's going on, right? So essentially throughout an entire super row, you can find a witness at most n over k times. And so that's the main idea for lowering the cost for finding these witnesses, is you group into these micro matrices and then just scan over the row again. So basically the same as we saw before, just a little bit more clever, this reduction here. And so essentially you just do the math, set k to be square root n, and you get the right round. You just count how many times does this happen, and so forth. It's the same as was done in the other paper. Right, so that basically shows that this is a combinatorial reduction, so that's the interesting part. So if you can do 3-sum in n to the 3½ minus epsilon combinatorially, then you can solve Boolean matrix multiplication in n to the 3 minus O of omega epsilon combinatorially. Right, so I think the last one I wanted to mention was this connection to 3 orthogonal vectors. I think it's sort of interesting too. So basically what we want to do is we want to use essentially we want to again use 3 orthogonal vectors to solve this figuring out whether there's an edge in this collection of induced subgraphs. It's the exact same problem, and if we can solve it into the 3½ minus epsilon, we can do the same reduction. All right, so we had this matrix, and you had some nodes, and some nodes, you had some edges, and the queries is again n subsets over here, n subsets over here that come in pairs, and you want to know if one of these pairs has an edge in them, and then we can just redo the rest of the reduction if we can solve this one in better than n cubed time. Okay. So maybe we want to do this using 3 orthogonal vectors, so maybe I should define the problem. So 3 orthogonal vectors is another one that you get from Seth, basically by partitioning your variables into 3 groups and doing all combinations of 3, doing all combinations, and then you're looking for, basically you have 3 sets, let's call them A, B, and C this time. And you're looking for a vector in A, a vector in B, and a vector in C, so that the bitwise AND of these vectors is 0. Right, so that's basically you have a bitwise AND of A, B, and C should be the 0 vector. Right, and this requires n cubed time under Seth. So the low bound we'll get here is not as strong, but at least it will relate the 2 problems that we're looking at. Right, so now I want to essentially use a solution for 3 orthogonal vectors to figure out on these, if one of these induced subgraphs has an edge in them. And so the idea is the same as before. Since you have these n copies of your rows and n copies of your columns, and you have the edges in the middle. You have n squared edges in the middle. And so what you do is, so for an edge between S and T, so you create a bit pattern. And so the first half of the pattern will be basically S written in binary, followed by S bitwise complement in binary. and then you do t, and you do t bitwise complement, and then you do all ones. Okay. So this is what you do for all the edges in the middle set. Okay. So now you go. So what do you do with the ith copy of an s of the vector s? So what you do is you go over here. So basically you write s complement s, write all ones, and now you write I complement. I'll argue why it works at the end. And finally up here, if you do for the ti, what you do is you have all ones in the beginning. Now you write t complement t, and you write I complement I. Okay, so what's the idea here of this construction? So basically what we want to argue is that whenever I select an edge, whenever I select a triple, they can only be orthogonal if the si and the ti come from the same I. So basically they have the same I. Right, because I may only use this one induced subgraph, and this is what the last part ensures. Right, this part, the AND of these three things, is the AND of these guys. And this will only be 0 exactly if these are complements of each other, both cases, right? That's the idea. These two will be 0 and these two will be 0. And this will not be the case if there was another index. Okay, so so this makes sure that I can, if I want an orthogonal pair, I can only use an si and a ti that came from the same subproblem. And the last part is, so I want to use an edge as well. And then here, again, essentially it's the same trick. I can only use an edge to get an orthogonal pair if the s aligns with the s and the t matches the t. That's the only way they'll be orthogonal. And so that's the full proof here. You have an orthogonal pair if and only if one of these n subproblems has an edge. And so the size of these bit patterns here, right, so there's n nodes here in each of these copies. So this is log n bits, this is log n bits, log n bits, and log n bits. And log n bits and log n bits. So essentially there's 6 log n bits in total in these vectors. And the instance size is, so n is basically n squared. So what you really have shown, right, so this is an instance of 3 orthogonal vectors of size n squared. So really the dimension is 3 log n, where you rescale the problem size. So I think it's also interesting to get such a fixed constant to show any hardness, that you actually, under the combinatorial Boolean matrix multiplication conjecture, you can't do n to the 3/2 minus epsilon if d is equal to 3 log n, and you believe the combinatorial Boolean matrix multiplication conjecture. So this is sort of a very tight bound on the size of the vectors. So I think that pretty much is what I wanted to say. So, hope I convinced you. Yeah, I don't know how well I'll be able to answer questions, but let's try. If anyone has any questions?
Yeah. I'm completely convinced.
Okay, that's good.
Well, because I mean, the first result about BMM and threesome, this is known.
Yeah, exactly.
But actually, I've never seen it explained this way before. It's such an excellent presentation. So.
Thanks a lot. That's good.
And it shows me it's very natural, actually.
Thanks.
What would be the dramatic consequence if you could do the last trick with just 2 vectors?
What?
I'm sure that things could fly, I just can't see it. I mean,
Oh, if this was not 3 orthogonal vectors, but 2, well, I guess then you would get a low bound of n to the 3/2 for orthogonal vectors, the normal version of the problem. Still not n squared low bound, but an n to the 3/2 low bound. I don't.
Also, for this case, when
Yeah, I guess you can actually do better in this.
it's less than,
Yeah, I suppose.
Yeah, you
look up what the actual
exactly, okay,
Yeah, so I guess that.
Yeah.
I guess there's a reason why it fails. Yeah. Thanks for listening.